Welcome back to the deep dive. You know, you wanted to unpack this whole giant planet formation thing.
Yeah,
And honestly, so do we.
it's a good
It's
one.
one of those big mysteries of astronomy.
Hmm.
How do these Jupiter-sized objects form?
Right,
And so we're going to dive into that today. I think this will be a couple-parter.
right.
And we're going to be looking at the paper Formation of Giant Planets by
Yeah.
Udine and Zhu.
Yeah, it's a really good review paper. It's really dense.
Very dense.
But they cover all the major ideas and the evidence and observations. So.
Yeah, it's a good one to use as a jumping off point.
Hmm.
So I guess the first place to start is, what do we actually know about our own giant planets?
Well, we have two very different kinds of giant planets in our solar system.
Right.
We've got the gas giants Jupiter and Saturn,
Right.
and we've got the ice giants Uranus and Neptune.
And they're different in that the ice giants have more heavy elements,
Yeah.
like proportionally.
Yeah, so if you were to like magically separate out all the different elements that make up Jupiter, it would be like 99% hydrogen and helium.
Right.
But for Uranus and Neptune, it would be maybe like, I don't know, 20% other stuff.
Okay, so a much more significant amount of heavy elements in those.
Okay. And that tells us something about how they formed.
Okay.
Another really interesting clue comes from meteorites.
Okay.
So we have these two classes of meteorites.
Uh,
Um, and they're basically separated by their carbon content.
oh, yeah.
So you have carbon-rich meteorites and carbon-poor meteorites.
Interesting.
And the best explanation for that we have right now is that Jupiter formed gradually
Okay.
through core accretion, and as it was forming,
Wow.
it blocked the exchange of material in the disk.
Between the inner and outer solar system.
Yeah, so all the carbon-rich material stayed out beyond Jupiter,
Okay.
and all the carbon-poor material stayed closer in.
Hmm. And that's why we have this difference in the meteorites we see today.
Sure.
Wow. It's amazing how we can piece together these stories from billions of years ago just by looking at the composition of rocks that fall to Earth.
I know, it's incredible.
But you said that's the best explanation we have. Are there other potential explanations for this meteorite dichotomy?
Oh, yeah, absolutely. So one idea is that the snow line migrated.
Right.
So the snow line is the distance from the star where water ice can exist.
Right.
And if that line moved around, it could have separated the carbon-rich and carbon-poor material.
Okay.
Another possibility is that the carbon-rich pebbles arrived late.
Like from the outer solar system.
Yeah, exactly. Or maybe there were like disk outbursts that heated up part of the disk.
Huh. So there are a few different possibilities, but it seems like the Jupiter formation explanation is the leading contender.
Right.
Go, well, that's our solar system.
Yeah.
But what about other planetary systems?
Yeah, so that's where things get really interesting.
Right, because we have all these exoplanets now.
Exactly. We have thousands of exoplanets that we know of now, and they've completely revolutionized our understanding of planet formation.
Yeah, like what have we learned from these exoplanets about giant planet formation?
Well, one of the most important things we've learned is that giant planets are most commonly found between 1 and 10 AU from their host star.
And AU, again, just for our listeners, is the average distance between Earth and the Sun.
Right.
Okay.
So that's kind of like the sweet spot for giant planet formation.
Okay, interesting. So, anything else we've learned?
Yeah, so we've also learned that giant planets prefer metal-rich stars.
And that means stars that have a higher proportion of elements heavier than hydrogen and helium, right?
Yeah, exactly.
So,
But here's the weird thing. That trend is reversed for binary stars.
really? So binary stars are less likely to have giant planets around them if the stars are metal rich?
Exactly. It's
Hey.
super counterintuitive.
That's wild. What's the explanation for that?
Well, it tells us that most giant planets probably don't form through disk fragmentation,
Okay.
which is the process that's thought to dominate in binary star formation.
So it seems like core accretion is the more likely explanation for most giant planets.
Yeah, the data really points in that direction.
Okay, so the metallicity preference is like a clue, a fingerprint that points us towards a specific formation mechanism.
Right.
Cool. Any other insights from exoplanets?
Oh, yeah, tons. So another really important clue is the mass distribution of giant planets.
Okay.
So the number of giant planets drops off sharply above about 10 Jupiter masses.
Okay.
And that's in contrast to the rising mass function of stellar companions,
Okay.
which are thought to form via disk fragmentation.
Right.
So again, this points away from disk fragmentation as the dominant process for giant planet formation.
Okay, so the mass distribution is another clue that favors core accretion.
Exactly.
Okay, what else?
Well, and another really cool finding from Kepler is the radius gap.
The radius gap.
Yeah.
What is that?
So basically, there's this gap in the distribution of planetary radii.
Hmm.
So there are very few planets with radii between about 1.5 and 2 Earth radii.
Okay.
Yeah.
So planets seem to avoid a certain size range.
Right. And it seems to be a dividing line between rocky planets with thin atmospheres
Uh-huh.
and planets with substantial gaseous envelopes like our gas giants.
Interesting.
Hmm.
So what's the explanation for this gap?
Well, there are two main competing theories. One is that the gap is formation-driven.
Okay.
So planets just don't form in that size range.
Okay.
The other is that planets do form in that range,
Uh-huh.
but then they lose their atmospheres due to atmospheric escape processes.
Interesting. So it's either that they don't form there or that they form and then lose their atmosphere.
Right.
Okay.
And figuring out which one is right is an active area of research.
Lots of unanswered questions still.
Oh, yeah, definitely. But I mean, we've come a long way. We have actual pictures of planets forming now.
Really?
That's amazing.
Yeah, there are these two protoplanets, PDS-70b and C,
Okay.
that have been directly imaged.
Wow. So
Yeah.
we're actually watching planet formation in action.
Yeah, it's incredible. That's wild. Okay, so we've got all these observational clues from our own solar system and from exoplanets.
Mm-hmm.
Now let's get into the actual formation mechanisms. So how do these giants actually form?
Well, as we've been kind of hinting at,
Yeah.
the leading theory is core accretion.
Okay, so let's break that down. How does core accretion actually work?
So it all starts with dust grains in the protoplanetary disk,
Okay.
which is the swirling cloud of gas and dust that surrounds a young star.
Right.
And these dust grains collide and stick together, and they gradually grow larger.
Okay.
But when they get to be about a meter in size,
Uh-huh.
they run into a problem.
Okay, what's the problem?
They start bouncing off each other or fragmenting upon impact.
Oh, wow.
We call this the meter-size barrier.
The meteor-sized barrier. So how do they overcome that?
Well, that's where things get even more interesting.
Okay.
There's this process called the streaming instability.
Okay.
And it's this really cool mechanism where the collective drag force of drifting pebbles on the surrounding gas causes them to clump together.
Interesting. So the pebbles are like creating their own traffic jam.
Exactly. And as these clumps grow denser, they eventually collapse under their own gravity.
Okay.
And they form planetesimals,
Okay.
which are like kilometer-sized building blocks of planets.
Okay. So we've gone from dust grains to pebbles to planetesimals. So now how do we get to a giant planet core?
Right. So the growth of these heavy element cores is crucial.
Okay.
And there are two main processes at play:
Okay, what are they?
planetesimal accretion and pebble accretion.
Okay, so planetesimal accretion, that's kind of the classic picture, right?
Yeah, that's kind of the more traditional view.
Yeah.
Where these planetesimals collide and stick together and gradually build up a larger and larger core.
Right. But isn't that really slow?
Yeah, it can be, especially at large orbital distances.
Okay.
But there's another process called pebble accretion.
Okay, and what's that?
And that's where a growing core can actually continuously sweep up pebbles that are drifting inward from the outer disk.
So it's like a cosmic vacuum cleaner sucking up all the pebbles?
Exactly.
Okay. And how does that compare to planetesimal accretion in terms of speed?
It can be much faster.
Okay.
So it allows cores to form even at large orbital distances.
Okay.
But there's a limit to how much a core can grow through pebble accretion.
Okay, why is that?
Because as the core grows, it starts to carve a gap in the disk, and that creates a pressure bump at the outer edge of the gap.
Okay.
And that pressure bump can trap pebbles.
Huh.
So the core effectively cuts off its own pebble supply.
So it's like it starves itself.
Yeah, basically. And this leads to the concept of the pebble isolation mass.
The pebble isolation mass.
Yeah, which is the mass at which a core can no longer effectively accrete pebbles.
I see. So there's this delicate balance between the speed of pebble accretion and then this eventual starvation of the growing core.
Right.
Okay. So we've got this core now, but it's still not a gas giant yet.
Right. We haven't even gotten to the gas envelope.
So how do we get from this solid core to a giant planet with a huge gas envelope?
That's the next step, and it's where things get really wild. It's a remarkable process, this transformation from a solid core to a gas giant, driven by the physics of gas accretion.
Yeah, and you mentioned before that there are like these two distinct stages in this gas accretion process.
Right.
The attached phase and the detached phase.
Right, exactly. So those are the two key phases.
So what exactly distinguishes those two phases? Like what's the difference between them?
So the key difference is the connection between the planet's growing gaseous envelope and the protoplanetary disk.
Okay.
So in the attached phase, the envelope is directly connected to the disk,
Okay.
allowing a smooth transition of gas from the disk to the planet.
So it's like it's still feeding directly from the disk.
Yeah, you can think of it that way.
Right.
It's like an extension of the disk itself.
Okay.
But the growth during this phase is actually regulated by cooling and contraction.
Okay. So why is the cooling and contraction so important in that phase?
Imagine the growing envelope like a hot air balloon.
Okay.
As it accretes more gas, it heats up, and it wants to expand outward.
Okay.
But to continue accreting and growing, the envelope needs to shed this heat and contract under its own gravity.
Gotcha. So the cooling is basically putting the brakes on the growth a little bit.
Exactly.
Okay. So then what factors are influencing that cooling rate?
Well, there are several factors. The core mass, the opacity of the envelope, and the temperature of the surrounding disk all play a role in how fast the envelope can cool.
Okay. And remind me again what opacity means in this context.
Right, so opacity describes how easily radiation can escape from the envelope.
Okay.
It's kind of like trying to see through a dense fog versus a clear sky.
Okay.
The fog has high opacity blocking the light,
Uh-huh.
while a clear sky has low opacity letting the light pass through easily.
Okay.
A higher opacity means the envelope traps heat more effectively and slows down the cooling process.
So lower opacity means faster cooling and therefore faster accretion.
Exactly.
Okay. Gotcha. And you also mentioned core mass. How does that factor in?
So a more massive core has a stronger gravitational pull, which compresses and heats the envelope.
Okay.
And that might seem counterintuitive.
Right, because you think more massive core, you'd think it'd be cooler.
You would,
Okay.
but a hotter envelope can actually radiate energy away more efficiently, leading to faster cooling.
So it's a delicate balance between all these different factors.
Exactly. It's like a cosmic balancing act.
Wow. And this all kind of leads into this idea of a critical core mass.
Right?
So what is the critical core mass and why is that so important in this whole process?
So the critical core mass is the minimum mass a core needs to reach for runaway gas accretion to occur within the lifetime of the protoplanetary disk.
Okay, so it's like a tipping point.
Yeah, basically.
Like once you reach that mass, then you can really start accreting gas like crazy.
Right, exactly. If a core doesn't reach this critical mass before the disk dissipates,
Uh-huh.
it won't be able to accrete enough gas to become a gas giant.
So it's a race against time.
It is.
Wow.
Yes.
So what happens once the core surpasses that critical mass?
That's when things really get going.
Right.
Gas accretion enters overdrive and becomes exponential.
Oh.
The envelope rapidly swells,
Mhm.
and eventually it detaches from the disk,
Yeah.
marking the transition to the detached phase.
All right, so in the detached phase, the planet is no longer directly connected to the disk.
Right.
So how does it continue to accrete gas?
So the detached phase is a much more dynamic process.
Okay.
So the gas no longer flows smoothly onto the planet.
Okay.
Instead, it flows dynamically,
Yeah.
often passing through a circumplanetary disk.
A circumplanetary disk.
Yeah,
Is that like a mini version of the protoplanetary disk just around the planet itself?
exactly. It's like a mini protoplanetary disk.
Okay.
And it's actually thought to play a key role in the formation of moons.
Oh, wow.
So yeah, they're really fascinating objects in their own right.
So it's like a whole other level of planet formation happening around this gas giant.
Right. It's like a nested system.
That's wild. Okay.
Yes.
But we've been talking about all this gas accretion in one dimension.
Uh-huh.
Assuming a spherical envelope. And that's probably a pretty big oversimplification, right?
Oh, yeah, absolutely. The real picture is much more dynamic and three-dimensional.
Okay. So 3D simulations have shown that gas flow around a forming planet is incredibly complex, far from the idealized spherical accretion that we often depict.
Right. So when you start looking at things in 3D, it gets really interesting.
So what does that 3D picture actually look like? And how does it change our understanding of gas accretion?
So imagine gas flowing in from the poles of the planet swirling around and then flowing back out from the equator.
Okay.
This creates a constant circulation of material, a sort of recycling flow,
Okay.
that mixes the cooler gas of the envelope with the hotter gas from the disk.
So it's like a cosmic whirlpool around this growing planet.
Yeah, that's a great way to visualize it.
Okay. But how does this recycling flow affect the cooling process that we were talking about earlier?
That's a key point. So these recycling flows can actually hinder cooling because they're introducing hotter gas from the disk back into the envelope.
Oh, wow.
It's like trying to cool down a hot drink while someone keeps stirring in warm water.
Gotcha. So it's counteracting the cooling.
Exactly.
Okay, so it's not just about the amount of gas available, but also the way that the gas is flowing and mixing and influencing the cooling.
Right. It's all interconnected.
And we need even more complex models to try and figure this all out.
Yeah, and to make our models even more realistic, we also need to consider the effects of radiation hydrodynamics.
Okay, radiation hydrodynamics.
Yeah.
So how does radiation come into play in all this?
Radiation plays a crucial role in transporting energy both within the envelope and between the planet and the disk.
Okay.
It can either aid or hinder cooling depending on a whole bunch of factors.
So it's not even straightforward whether radiation is helping or hurting the cooling process.
Right. It depends on things like the opacity of the gas and dust, the temperature gradients, and the geometry of the system.
It just gets more and more complicated.
It does, but that's the nature of complex systems.
Yeah, guess so. Okay, well, we've been focusing a lot on core accretion, but what about the other theory, the disk instability hypothesis?
Right. So the disk instability hypothesis is a totally different way to form giant planets.
Yeah.
Instead of building up a core gradually,
Mm-hmm.
this theory proposes that giant planets can form directly from the gravitational collapse of a massive and unstable protoplanetary disk.
So it's like a sudden collapse rather than a gradual buildup.
Right.
So instead of slowly building up a core like brick by brick, this theory suggests that a giant planet could form in one fell swoop, like a cosmic flash mob of gas and dust coming together.
Pretty much.
Whoa.
Yeah.
Okay, so what kind of conditions are needed for this to actually happen?
So for this to work, the disk needs to be sufficiently massive.
Okay.
It needs to cool rapidly,
Uh-huh.
and it needs to have a low resistance to gravitational collapse.
Okay, so what are the factors that determine whether a disk is going to fragment and collapse in this way?
So there are a few key factors.
Huh.
The disk's surface density, its temperature, its opacity, and the rate at which it's accreting material from its surroundings.
Okay.
And a key parameter that astronomers use to assess the stability of a disk is something called Tumor's Q.
Tumor's Q.
Okay.
Sounds like a secret code for unlocking the mysteries of disk instability.
It kind of is. Think of it like a spinning top.
Right.
If it's spinning fast enough, it stays upright.
Right.
But if you slow it down, it starts to wobble and eventually falls over.
Okay.
Tumor's Q is a measure of how close a disk is to that wobbling, unstable point.
Gotcha. So a low Q value means the disk is more likely to fragment.
Exactly.
Okay. But you mentioned earlier that simulations suggest that even when fragmentation occurs, most of the resulting objects don't actually end up as giant planets. So why is that?
Well, it's a dangerous journey for these newborn giants, so
Oh.
that they often undergo rapid migration,
Okay.
spiraling inward towards the host star.
Uh-huh.
And when that happens, they might get tidally disrupted or even ejected from the system altogether.
Oh, wow. So it's like a cosmic game of survival.
It is.
Okay. And even if they survive migration, they might accrete so much gas that they end up as brown dwarfs rather than planets.
Right, so they kind of overshoot the mark.
Yeah. So it seems like the odds are stacked against them.
They are, and that's one of the reasons why core accretion is generally favored as the dominant mechanism for giant planet formation.
Okay. So core accretion, while complex, seems like a more reliable pathway.
It does.
But is there any other way to distinguish between these two formation scenarios?
Yeah, there is. So there's this key property of giant planets that can give us clues about how they formed.
Okay, what's that?
It's called initial entropy.
Okay, you've piqued my curiosity now. What exactly is initial entropy, and why is it so important for understanding how these giant planets formed?
So in the simplest terms, initial entropy is a measure of a planet's thermal energy content right at the time of its formation.
Okay.
You can kind of think of it as a planet's starting temperature. So a planet that's born hot will have a higher initial entropy than a planet that's born cold.
So it's kind of like a fingerprint of its birth environment.
Exactly. And this fingerprint can have really big implications for the planet's evolution,
Uh-huh.
influencing its luminosity, its cooling rate, even its atmospheric composition.
So how do we actually categorize giant planets based on their initial entropy? Like, is there a system?
Yeah, so we broadly classify them into two categories, hot starts and cold starts.
Okay.
Hot starts refer to planets that have high initial entropy,
Okay.
typically above 9.5 keoB per baryon.
Okay, hold on, KB per baryon. I'm lost. What is that?
Right, so that's just a unit of measurement for entropy per particle.
Okay.
In this case, it refers to the entropy per baryon, which is a type of subatomic particle.
Okay.
You can kind of think of it as a way to quantify the disorder or randomness of a system at a microscopic level.
Okay, so hot starts are the ones that have more entropy per particle than cold starts. Okay, but how does this whole hot start, cold start thing relate back to those formation models we've been talking about?
Right. So initially it was thought that core accretion would naturally lead to cold starts,
Okay.
while disk instability would favor hot starts.
Okay. And that makes sense because you'd think something that forms through this sudden collapse
Right.
would be a lot higher than something that slowly accretes.
Right. It seems very intuitive,
Yeah.
but our understanding has evolved a bit since then.
So what have we learned since then that's changed how we think about this?
So recent studies have shown that even in core accretion, the initial entropy can be quite high.
Really?
Yeah.
So you can get warm or even hot starts even in that scenario.
Yeah, exactly.
Wow, I thought core accretion was supposed to be this slow and gentle process.
It is, but there are a couple of key factors that can boost that initial entropy even in core accretion.
Okay, what are those factors?
So one is the accretion rate.
Okay.
If a planet accretes gas really rapidly,
Uh-huh.
that process generates a lot of heat. So the faster the accretion, the hotter the start.
So it's not just about the end product, it's also about how fast you get there.
Exactly.
Interesting. Anything else?
Yeah. So another factor is the efficiency of the accretion shock.
Okay.
So that's the region where the infalling gas slams into the planet's envelope.
Right.
Yeah.
I can imagine that generates a lot of heat.
It does. And the efficiency with which that shock radiates away energy can really influence the planet's final entropy.
Okay.
A less efficient shock leads to a hotter start.
So it's like trying to slow down a runaway train?
Mm-hmm.
Like the more efficient the brakes, the cooler the train stays.
Yeah, that's a good analogy.
Okay, so that's really interesting. So even core accretion can produce planets with a pretty wide range of initial entropies.
Right.
So does that mean that we can't use initial entropy to distinguish between formation mechanisms anymore?
Not necessarily. It's not a foolproof method,
Oh.
but initial entropy can still provide clues about a planet's formation history.
Okay, so it's
Yeah.
still useful information.
Yeah. For example, a planet with a hot start must have undergone a period of really rapid accretion at some point.
Interesting. So it's almost like a fossil record of the planet's early evolution.
Exactly. And the initial entropy also has implications for a planet's present and future evolution.
Okay.
Influencing things like its luminosity, its cooling rate, its atmospheric properties.
Wow. Okay, so initial entropy is a really powerful tool for understanding these planets. But how do we actually measure it? We can't exactly stick a thermometer into a gas giant that's light years away.
That's true. Direct measurement is impossible,
Yeah.
but we can infer a planet's initial entropy through a combination of observations and modeling.
Okay.
For example, the planet's luminosity and atmospheric composition can provide clues about its thermal history.
So we're using indirect evidence to piece together the puzzle.
Exactly. We're like cosmic detectives.
I love that.
Mm-hmm.
Well, this has been a truly fascinating exploration of giant planet formation. Thank you for guiding us through this incredibly complex and ever-evolving field.
My pleasure. It's a topic I'm really passionate about.
And to our listeners, thank you for joining us on this deep dive into the fascinating world of giant planet formation. We hope you learned something new and maybe even sparked some new questions in your mind. Until next time, keep looking up and keep wondering about the wonders of our universe.